So for the next two lessons, the topic is called equivalent resistance. For this lesson, I'm going to focus on strictly series circuits and strictly parallel circuits. And in the next lesson, we'll do mixed circuits. So first of all, this is a mixed circuit here, actually, but I'm going to use it to try to explain what I mean by the term equivalent resistance. So the big picture. So I've got a power source that I chose. So I chose a 19-volt battery. And then I'm going to connect that power source to an entire circuit. The circuit can have all sorts of things in it. This one has some light bulbs, and it has a resistor as well. They can be connected in all sorts of different ways. This is an example of a mixed circuit, but I could do series, I could do parallel. But the question is, when I connect this entire circuit to this 19-volt battery, what's the current going to be? Okay, so I've got an ammeter here. Right now it's a question mark. It's going to measure the current that's flowing through the battery. Another way of asking that question is, how much resistance is this 19-volt battery going to face when this entire circuit is connected? Okay, so how much resistance is this battery going to face when connected with this entire circuit? And so basically what I'm doing in this lesson is trying to teach you how to combine these numbers. So these light bulbs have their own individual resistance. We've got a couple of 10 ohm resistance light bulbs. We've got a 20 ohm resistance light bulb. And we've got a 15 ohm resistance resistor. So all of these loads have their own resistances. How do we combine them into just one single number, which will be the total resistance that the battery is going to face when it's plugged into the circuit? That's the goal, and that's called equivalent resistance. Okay, it's equivalent resistance is a single value for the resistance of the circuit as a whole. All right, and that's what the battery is going to face. Once we know that equivalent resistance, once we know how much resistance this 19 volts will face, we can then use Ohm's law to calculate the current. Okay, Ohm's law is voltage divided by resistance. So this circuit, I'll come back to it in the next lesson, but for this lesson, we're going to talk about series only and parallel only. So here's a series circuit I made in the circuit construction kit online, and it's series because there's only one path. Okay, there's no junctions. Right now it's not connected yet to the battery. So I've got a 10 ohm light bulb, a 12 ohm resistor, and an 8 ohm light bulb. I'm going to plug them all into this battery. And the question is, how much total resistance is this 9-volt battery going to experience? And when it's a series circuit, the formula is really simple and straightforward. The equivalent resistance, denoted by Req, is simply equal to the sum of all of the individual resistances. So N stands for like the last resistor. There could be any number of resistors. Our example just has 3. So for our example, the equivalent resistance would just equal to R1 plus R2 plus R3, the sum of the 3 resistances. So that's calculated in this text box here. So the circuit has 3 loads in series. The equivalent resistance is 10 plus 12 plus 8. That equals to 30 ohms of total resistance. So this 9-volt battery is going to face 30 ohms of resistance. And with that information, we can calculate the current using Ohm's law. So current equals voltage divided by resistance. So that would be 9 volts divided by what we calculated, 30 ohms. And 9 divided by 30 equals 0.30 amps. Which is what is confirmed by the simulation. The ammeter right here reads 0.30. I'll go back to the circuit construction kit and I'll connect it up. and you'll see that it equals to 30 amps. So 0.3 amps. So that's the gist of it. When we design circuits in real life, we know how much voltage the power source is giving out. Okay, we know how much voltage the batteries are. We also know how much resistance each individual component has. Okay, when you buy light bulbs, you can read the information on it, and with that information, you can know how many ohms the light bulbs are. And same with the resistors. You buy a pack of resistors, and they're color coded. And the colors, if you know the system for reading the colors, you can know how much resistance each resistor has. So when we design circuits, we know the voltage, we know all of the individual resistances. And now with our formulas, we're able to calculate equivalent resistance, and we're able to calculate the current that runs through the battery. And that turns out to be kind of important because certain components and even certain wires that you use can only withstand a maximum amount of current. Okay, so wires can only withstand a maximum amount of current. So it's important to be able to calculate and predict how much current there is going to be in the circuit, and make sure that it's lower than the maximum that the wire can withstand. Similarly, devices like light bulbs or more advanced components, some of them require a minimum current in order to function. All right, so if the current's too low, whatever you're trying to operate won't function properly. Maybe your light bulb will barely give off any light if the current's too low. So it's important to be able to calculate this. And how can you change the current though? How can you change the current? Well, what you do, there's two things you can do to change the current. You can either change the value or change the resistor you use. Okay, so you buy a package of resistors. They're all sorts of different resistances. If you need the current to be smaller, so right now the current's 0.3 amps. If you need the current to be smaller, then you're probably going to replace this resistor with a higher resistance. And if you need the current to be bigger, you replace the resistor with one of lower resistance. Right, and you see the current going up there. Another thing you can do is you can change the battery. Right, if you need a higher current, you use a battery or a power source with higher voltage. If you need a lower current, you can use a battery with lower voltage. So that's how you can, that's all you can really do. When you're designing circuits, you can choose the voltage source, you can choose the resistances, and you can also choose how you connect them, whether it's series or parallel. And with all of that, you design a circuit that has an ideal current. Okay, I'm going to go to parallel circuit now. Oh, sorry, no, I'm not. Series circuit example continued. So this is just relating back to the previous lesson of circuit puzzles. So we know, with this picture, we know various informations. Okay, that's all written in black here. We calculated this 30 ohms resistance. So for the circuit puzzle, I said we would cross that out until a future lesson. Well, that future lesson has arrived. The battery's resistance, we're going to write in whatever you calculate for the equivalent resistance there. Okay, and everything else in black has all been calculated from the previous slide or given in the diagram. And then that'll leave us some blank spaces, which I've filled in red. Okay, so I went ahead and used the tools for circuit puzzles, which are KCR, KVR, and Ohm's law. Use those to calculate everything that's in red here. So we can combine this lesson of equivalent resistance with the previous lesson of circuit puzzles to find out all the information we need to know about any circuit that we design. All right, now I'll go to an example of a parallel circuit. So The formula for a parallel circuit's equivalent resistance is actually quite a bit more complicated. It's 1 over equivalent resistance equals 1 over the first resistance plus 1 over the second resistance, etc., all the way up to 1 over the last resistance. So I'm going to try to calculate that for this circuit that I have right here. I got a 3-volt battery that I'm going to connect to a parallel circuit with 3 light bulbs in parallel. The light bulbs have resistances of 5 ohms, 10 ohms, and 15 ohms. These 0 ohms, these are switches. Okay, I added switches because I want to show you something a bit later with the switches. We'll just ignore the switches for now. Okay, so how do I get the equivalent resistance for this whole circuit? It's in parallel, so I'll use this parallel formula. I've done that on this next slide here. All right, so first step is to just write out the formula and plug in the values of the resistances. So 1 over Req will equal to 1 over 5, which was the first resistance of the first light bulb, plus 1 over 10, plus 1 over 15. Okay, that's the first step, to write out the formula with the numbers plugged in. Then I gotta add these 3 fractions together. So when you add fractions, it's a good idea to make a common denominator. So that's what I did for the second line here. The common denominator of 5, 10, and 15 would be 30. So I just rewrote all fractions to be out of 30. That way I can add the numerators together. 6 plus 3 plus 2 is 11. So this equals 11 over 30. So 1 over Req equals 11 over 30. Now, what you do to one side, you do to the other side. So what I can do at this point is take the reciprocal of both sides. The reciprocal of 1 over Req is Req over 1, or just Req. And that's going to equal to the reciprocal of 11 over 30, which is 30 over 11. And that equals to 2.727272 repeated. But I just underlined the 2 sig figs that it's supposed to be. So the equivalent resistance is 2.7 ohms, meaning when I plug this circuit into this 3-volt battery, the 3-volt battery is going to face 2.7 ohms of resistance. And I can use Ohm's law right here to calculate the expected current value. So 3 volts divided by 2.7 ohms is 1.1 amps, which is what the simulation gives me when I actually plug it in. So that's how you calculate the equivalent resistance in parallel. Again, I can go on, fill the information I just calculated and what I'm given in a table, and complete the whole circuit puzzle. All right, so one thing I want to point out is that in series, the equivalent resistance gets bigger as you add more resistors. Okay, as you add more resistors, the equivalent resistance gets bigger, so the battery is going to face a heavier resistance and the current's going to get smaller. However, in parallel, it's actually the complete opposite. Notice our answer of 2.7 ohms. 2.7 ohms is what the battery faces, but 2.7 is smaller than 5. It's smaller than 10. It's smaller than 15. It's smaller than any of these individual resistances. So when you add extra pathways, in parallel, you're actually going to lower the equivalent resistance. Think of it as a city roads. You have traffic jams, but if you build extra highways, that can relieve some of the traffic jams and allow the current to get higher. So that's what I wanted to show you with these switches is, so I open these 2 switches. So I just have one light bulb working. Look at the current, it's just 0.6. When I add a second pathway, my current actually got bigger. And I'll add a third pathway, current got even bigger.